Okay, in this video we're going to be looking at how to estimate a population mean. So we'll be writing a confidence interval estimate for a population mean. And also we'll look at the required sample size when we're dealing with a population mean. Okay, so what we'll talk about first is estimating a population mean. And I'm just going to write this as estimating a population mean. In this situation, we're only going to be dealing with the fact that sigma, which is your population standard deviation, is not known. Because the reality is this: we rarely know what the population standard deviation is. If we knew what the population standard deviation is, then we would pretty much get an idea of what the population mean would be, which will be useless in estimating a population mean. So reality is this: our population standard deviation is unknown, and the only thing we'll be focusing on is just that particular concept. Now, when we were estimating a population proportion, your p hat was your best point estimate for the population proportion. In this situation, your sample mean, which is denoted by x bar, is going to be the best point estimate of the population mean. Okay. And that population mean is the Greek letter mu. So your best point estimate for the population mean will be just simply the sample mean, which is what we'll be focusing on. Okay. Now, in this case, when we're dealing with a estimate of a population mean when the sigma is unknown, we're going to be using a different type of distribution, and that's called the student t distribution. Okay. Now, where did this come from? It actually came from a statistician by the name of William Gossett, who worked at a brewery called Guinness Brewery, and he had some research that he wanted to release, and the company would not allow them to release any type of research. So what he did was he released that research that he had under a pseudonym or a fake name, which is called student. So that's where student t distribution came from. Okay. Now, in a student t distribution, it's going to be the distribution of this. And it's going to be lowercase t is equal to x bar minus mu divided by s over the square root of n. Okay. So here x bar is going to be your sample mean, mu is the population mean, lowercase s is your sample standard deviation, and n is the sample size. Okay. So that's the student t distribution of all sample sizes n. And it can be referred to as just simply the t distribution. Okay. And in a student t distribution, you have something called degrees of freedom. So here's another definition. Degrees of freedom is just simply abbreviated as DF. Okay. Here the degrees of freedom is this. That's the number of sample values that can vary after certain restrictions have been imposed. Okay. That's the number of sample values that can vary after certain restrictions have been imposed. Like, for example, let's say we have 5 tests throughout a semester. You know your score is on 4 of the tests. But if you wanted to make at least 80, an average of 80, then that last test has to be fixed. It is a fixed value that you must make in order to get an average of 80. The other 4 can vary, but the 5th test has to be a restricted value for you to get an average of 80. So that's what we mean by degrees of freedom. Okay, and to find degrees of freedom is just simply the sample size minus 1. Okay, you take your sample size and you subtract 1 from it. Okay, and also, now when we were estimating a population proportion, we also talked about critical value. Now in this case, that critical value was a z-value for your population proportion. But for a population mean, when sigma is unknown, the critical value is now t sub alpha over 2. And we can find this using, and for those of you who are taking my class, take table A-3, or for those of you who are just watching this, it's going to be this table, the t-distribution of critical values. I might need to bring this down so you can see the heading. So here, this is what the table A-3 looks like. It's t-distribution critical t-values. On the left-hand side, you see the degrees of freedom. There are 2 rows on top. One is the area in one tail. The other one is the area in 2 tails. Since we're dealing with a confidence interval, we're only going to use the area in 2 tails. And usually the confidence interval is given as a percent. So you're going to have to do 1 minus that confidence interval to get that alpha level, which is going to be one of these here. So you use the decimal value in the area in 2 tails column, and then your degrees of freedom, which is n minus 1, read across and down, and you'll get the critical t value. Okay? And also, one more thing about table A-3, which is this table here. If you do not find the number of degrees of freedom in this table, you must use a conservative value, and that's using the next lower number of the degrees of freedom found in that table. Okay, because in this case here, if you look at it, when you get down to 40, then it jumps to 45, and then 50, and then 60, 70, 80, and then it gets to the more bigger numbers here. So you have to use a conservative number if you're using this table. The other option would be just using the technology, like StatDisk or your TI-83 or 84 Plus calculator, because you can get a more accurate critical t value using technology than you would with table A-3. Okay. Alright, next we'll go ahead and go into the confidence interval for estimating the population mean. Okay, so now, this is confidence interval. Estimate for a population mean, and I'm just going to say for mu, and this is with sigma not known. Okay. Now in this case, there are only 2 requirements for this particular construction of a confidence interval. One of them is, again, you must have a simple random sample, and that's where samples of the same size have an equal chance of being selected. And then second, either the population is normally distributed. You must be told that the population is normally distributed, or your sample size, which is n, must be bigger than 30. So one or the other must be satisfied in number 2. You know you have to have a simple random sample, but in number 2, either you have a normal distribution, a population that's normally distributed, or your sample size must be bigger than 30. Okay, so now, here's the format. The format is this: x bar minus the margin of error, and that's less than mu, and less than x bar plus the margin of error. Okay, now in this case, your margin of error is this: t of alpha over 2 multiplied by s divided by the square root of n. That's going to be your format. You already know x bar is your sample mean, and E, if you recall in the other video for the confidence interval estimate for your proportion, that's your margin of error. Okay. T of alpha over 2 is your critical t value that you'll get from the table. Lowercase s is your sample standard deviation. And n, sample size. Okay. Okay. All right, now for the round-off rule, and I'm going to put this set of notes here for the round-off rule. Now, when you're constructing a confidence interval from the original set of data values, you round the confidence interval limits to one more decimal place than is used in the original set of data. But mainly in this case, you'll be given summary statistics, usually n, x bar, and s. So in that situation, you'll round your confidence interval limits to the same number of decimal places used for the sample mean. In other words, if your sample mean is to one decimal place, you round your limits off to one decimal place. Okay. And then next is the procedure for constructing a confidence interval for mu. You want to verify that the two requirements are satisfied, meaning simple random sample and either you have a normally distributed population or n is bigger than 30. When sigma is unknown, as it is in this case, you're going to use n minus 1 degrees of freedom. And use technology or the t-distribution table to find the critical t value that corresponds to that desired confidence level. And then evaluate the margin of error using that formula: E is equal to t of alpha over 2 times s over the square root of n. And then use the value of the calculated margin of error and the value of the sample mean to find the values of your confidence interval limits. That's x bar minus e and x bar plus e. And you'll use mainly this first format. And there are others like x bar plus e plus or minus e, and then this interval notation x bar minus e and x bar plus e. And of course you use that round off rule to round your confidence interval limits. Okay. And let me remind you of the interpretation of your confidence intervals. Okay, because we talked about this when we were doing the confidence interval for a proportion. So if you have 58.1, which is less than mu, and less than 63.3 with 95% confidence, for example, the correct interpretation would be this. We are 95% confident that the interval from 58.1 to 63.3 actually does contain the true value of mu. Okay, and these next three are the incorrect ways of doing it. There's a 95% chance that mu will fall between 58.1 and 63.3. That's the incorrect way of doing it, because mu is a fixed value. Your population mean is either going to be within that interval or it won't be within that interval. And then 95% of all data values are between 58.1 and 63.3. That's also an incorrect interpretation. And 95% of all sample means fall between 58.1 and 63.3. That too is an incorrect interpretation. Okay, so do be very careful on how you interpret your confidence intervals for a mean. Okay, now let's look at some examples of just this. And by the way, well, before we do, let me talk about this right here, because the first three examples are going to be dealing with this particular chart. You want to find out if sigma is known. If it is, then you ask yourself the next question. Is the population normally distributed? If it is, then you use the z, or the normal distribution. If it's not, then ask yourself, is n bigger than 30? If it is, you use the normal distribution. If it's not, then you'll have to use other methods, not like non-parametric or bootstrapping methods, which we will not discuss in this course. Now, but if sigma is unknown, which is usually the situation, then ask yourself this question. Is the population normally distributed? If it is, then you're going to use the t-distribution. If it's not, then the next question you ask is n bigger than 30? If yes, use the t-distribution. If no, then we use the other methods, non-parametric or bootstrapping methods. So the first three examples are like that. So let me pull those up. So let's start with this one. You're going to do one of the following as appropriate. Find the critical value c of alpha over 2, or the critical value t of alpha over 2. State that neither the normal, or state that neither the normal nor the t-distribution applies. In this case here, you have a confidence level of 98%. Your sample size, n, is 25. Sigma is known. The population appears to be very skewed. Okay, so let's look at that flow chart. Okay, is sigma known? Yes, it is. And then we ask ourselves, is the population normally distributed? We were told that their population appears to be skewed, so that's a no right there. And then we ask the question, is n bigger than 30? In this case, that's no. So they're saying use non-parametric or bootstrapping methods. So to answer that question, it's going to be neither the normal nor the t-distribution applies. That will be option C. Neither the normal nor the t-distribution applies. Okay. So that flowchart will help you answer the other questions. Here's another example. Let's say, to construct a confidence interval using the given confidence level, do whichever of the following is appropriate: the critical t value or the critical z value, or neither. We got 95% confidence. Your sample size N is 300. Sigma is 18.0. The population appears to be very skewed. In this case, here sigma is known. So that's a yes. That's the population normally distributed. Again, in this case, well, in this case, that's no, because it says that it's skewed. So that's a no there. Is N bigger than 30? Well, our sample size was 300, so that's a yes, so we use the normal Z distribution. So in this case here, we're going to use that critical Z value. So, your critical value, which is this case, Z of alpha over 2, that's 1.96. If you recall, with the critical Z value, I gave you a table that has something to do with those critical Z values, where Z of alpha over 2 would give you, for the 95% confidence interval, it will be 1.96. And I can pull that up for you. Here, 95% confidence, your Z value, critical Z value, 1.96. Okay. Alright, the next example. Again, you're going to do one of the following, either the critical Z value or the T value or neither. The confidence level is 99%. Your sample size is 20. Sigma is 23.9. The population appears to be normally distributed. Okay, so let's go back to the flowchart. Now here, sigma is known, so that's a yes. The population is normally distributed, that's also yes. So here we go down here and use that normal Z distribution. Okay, so in this case, we're going to get a critical Z value. And that's Z of alpha over 2. And again, this is a 99% confidence level, so at 99%, your Z value is 2.575. So Z of alpha over 2 will be 2.575. Okay. Alright, next we need to look at some examples of finding the confidence interval estimates. Okay, so in this case here, here's the next example. A data set includes 110 body temperatures of healthy adult humans, for which X bar is 98.0 degrees Fahrenheit and S is equal to 0.72 degrees Fahrenheit. Complete parts A and B below. What is the best point estimate of the mean body temperature of all healthy humans? Okay, in this case, we know that the best point estimate has to be the sample mean. And that sample mean is given to us as 98.0 degrees Fahrenheit. So this represents your best point estimate. Because we always said that the best point estimate for a population mean would be the sample mean. And that's given to us in that problem. X bar is 98.6 degrees. 98.0 degrees Fahrenheit, I'm sorry. Now part B, using the sample statistics, construct a 99% confidence interval estimate of the mean body temperature of all healthy humans. Do the confidence interval limits contain the 98.6 degrees Fahrenheit? What does the sample suggest about the use of 98.6 degrees Fahrenheit as the mean body temperature? Okay, so now, if we have a 99% confidence, That means this. We look under the table, where we look under that critical t-value or the t-distribution table, where in the area in two tails is this, 1 minus 0.99, which will be 0.01. And also, we need our degrees of freedom, which is, of course, n minus 1. N is the sample size of 110. 110 minus 1 is 109. Okay, so your degrees of freedom is 109. Okay, now we need to find T of alpha over 2 using that table. Now, unfortunately, we're not going to find 109 in this table. So we're going to need to use a conservative value of 100. So 100 is here. Now, let me bring this down a bit. That alpha in two tails that we looked for was 0.01. That's going to be this first column right here. So follow along with me with this first column, and then go down to 100. That critical t value, okay, here's 100. And if you go across to that first column of 0.01, under the part where it says area in two tails, that will be 2.626. Okay? So here, T of alpha over 2 is going to be 2.626. Okay? So that's how we read the critical t value table, or the t distribution table. Okay, now from that we can find the margin of error. Okay, your margin of error is this. That's T of alpha over 2 times S divided by the square root of n. Your T, we found that out to be 2.626 times S, the population standard deviation, that's given to us as 0.72 in this problem. So here, that's what S is equal to, 0.72 divided by the square root of n. And n is 110, not the 109. The 109 represents your degrees of freedom. Your n is your sample size of 110. Okay, so here we can type all of this into the calculator. So here's what we have. 2.626 times 0.72 divided by second x squared for the square root of 110, close parentheses, and then hit enter. And I'm going to round this off to 4 decimal places, so this will be 0.1803. That's going to be your margin of error. 0.1803. Okay, now we got our margin of error. We know what x bar is. So now all we need to do there is just construct our confidence interval from here. And that's going to be your x bar minus e, that's less than mu, and less than x bar plus e. In this case, your x bar was 98.0 minus e, which is 0.1803, and that's less than mu, and less than x bar is still 98.0. This time it's going to be plus 0.1803. So now 98.0 plus 98.0 minus 0.1803 will be 98. Now I'm saying 98.2 because in our sample mean is to 1 decimal place. So the limits must be rounded to 1 decimal place. So it'll be 98.2. That's less than mu and less than I'm sorry, this should be 97.2. I'm subtracting. Okay, so this is 97.2. And the upper limit will be 98.2. Okay. Now, it all depends upon what the homework tells you to do. It tells you to round to so many decimal places, so whatever number of decimal places you need to round out to, that's what you'll do. Okay? So 97.2 and 98.2 represents the confidence interval limits. We can interpret that by saying that we are 99% confident that the mean body temperature of all healthy humans is between 97.2 and 98.2. Now, does the confidence interval limits contain 98.6? In this case, you can see 98.2 is the upper limit, 98.6 is outside that limit, so the answer there would simply be no. And what does the sample suggest about the use of 98.6 as a mean body temperature? Here, that sample tells us that your mean body temperature, or the true mean body temperature, is less than 98.6. Okay, because here's what the limits are. So that true mean body temperature is between those two. That means that that true mean body temperature must be less than 98.6. Okay. All right, let's look at another example of a confidence interval estimate. And in this case, in a study designed to test the effectiveness of magnets for treating back pain, 40 patients were given a treatment with magnets and also a sham treatment without magnets. Pain was measured using a scale from 0, meaning no pain, to 100, meaning extreme pain. After given the magnet treatments, the 40 patients had pain scores with a mean of 12.0 and a standard deviation of 2.1. After giving the sham treatments, the 40 patients had pain scores with a mean of 10.4 and a standard deviation of 2.5. And here you want to complete parts A through C below. So in part A, we're going to construct a 95% confidence interval estimate of the mean pain score for patients given the magnet treatment. And then part B will be the same confidence interval estimate, 95%, for patients given the sham treatment, and then we'll compare the results, which is part C, to find out if the treatment with magnets appear to be effective. So part A is our confidence interval estimate. Okay, we got 40 patients, so your sample size N is 40. For those who got the magnet treatments, X bar was 12.0 and the standard deviation was 2.1. And this is for the magnet treatments. Okay. And we're dealing with a 95% confidence level. And this is for a mean. So your area in 2 tails is this. 1 minus 0.95, which will be 0.05, which is what you'll be looking for in the area in 2 tails row. And then your degrees of freedom is N minus 1, which means 40 minus 1, which is 39. So in the table, we're going to be looking at 39 and 0.05 in 2 tails to find out what T of alpha over 2 is going to be. So 0.05 is this middle column right here. So I'm going to scroll down to find 39. So 39 is right here. And I'm going to read across to 0.05 and see that it's going to be 2.023 as our critical T value. So 2.023. is your critical t-value for 39 degrees of freedom and 0.05 in the area in two tails for 95% confidence. Okay, and from that we can find the margin of error. So here the margin of error is this, t of alpha over 2 times s divided by the square root of n. So t of alpha over 2 will be 2.023 times s, that's 2.1, divided by the square root of n, that's the square root of 40. And here we can use our calculator. So in this case, 2.023 times 2.1 divided by the square root of 40. Then hit enter. And I'm going to round this off to 2 decimal places, so it'll be 0.67. So your margin of error will be 0.67. So with our margin of error given and our mean given, we can go ahead and do the confidence interval estimate. So here, this will be x bar minus e. That's less than mu and less than x bar plus e. Now in this case here, your x bar was 12.0 that was given to us in the original problem. Minus e, we found that out to be 0.67. That's less than mu, less than 12.0 plus 0.67. Okay, now 12.0 minus 0.67 rounded to 1 decimal place, that's 11.3. Because our sample mean is to 1 decimal place. And then less than mu and less than 12.0 plus 6.67 will be 12.7. Rounded to 1 decimal place as well. Because our limits, we have to round to the same number of decimal places as our sample mean. Here the sample mean was to 1 decimal place. So our limits are rounded to 1 decimal place in the confidence interval. Now we can say here that we are 95% confident that the mean pain score for patients given the magnet treatment will be between 11.3 and 12.7. Okay, so that was part A. Alright, part B. Construct a 95% confidence interval estimate of the mean pain scores for patients given the Sham treatments. So for the Sham treatments, there were 40 patients. So N is 40. That sample mean was 10.4, and the sample standard deviation was 2.5. Okay, now, we still have a 95% confidence interval, which is still 0.05. The degrees of freedom will still be 39, so our critical t-value, or t of alpha over 2, is still going to be 2.023. Okay, because we have the same confidence level of 95%, so we change that to 0.05. We still have 40 data values, so the degrees of freedom will still be 39. So 39 degrees of freedom and 0.05 in the area in two tails will be 2.023. Okay, so the margin of error is t of alpha over 2 times s divided by the square root of n. And here we got 2.023 times s. This time is 2.5 divided by the square root of 40, which is what n is. So in this case here, 2.023 times 2.5 divided by the square root of 40. And this is 0.799660963. To 2 decimal places, it'll be 0.80. So your margin of error is 0.80. And from that, we can do our confidence interval, because we know what x bar is, we know what our margin of error is. So in this case here, that's x bar minus e, and that's less than mu and less than x bar plus e. So x bar is going to be 10.4 minus your margin of error of 0.80. That's less than mu and less than, again, 10.4, this time plus 0.80. And then we subtract and then add. 10.4 minus 0.80 would be 9.6. That's less than mu, and less than 10.4 plus 0.80 would be 11.2. Okay. So if we were to interpret this, that means we can say that we are 95% confident that the mean pain score for patients given the sham treatment is between 99.6 and 11.2. Okay. So here, in this case here, part C, we need to find out, do the treatments with magnets appear to be effective? Well, as you can see here, let me pull down this confidence interval estimate. You can see here that these two confidence intervals do not overlap. There is no overlap in these two. Okay, if there was an overlap, then we can't compare those two. Okay, now by looking at this, we can see that the magnet treatments are less effective than the sham treatments, because the intervals of pain, as you can see, those limits for the pain given the magnet treatments are larger than the intervals or the limits for the sham treatment. Okay, and I do need to mention this was the sham treatments here. So we can say that the treatments with magnets appear to be less effective. Okay, so let me add this. The magnet treatments appear to be less effective than the sham treatments. Okay. 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 Alright, now there is one last thing that I need to cover in this section, and that is the required sample size for estimating the population mean. Okay. In one of the videos, we talked about how to determine a sample size for a population proportion, to estimate a population proportion. So this is determining a sample size to estimate mu. Okay. So let's just say determine a sample size to estimate mu. Alright, in this particular situation here, the only requirement is that you must have a simple random sample, and the formula for finding the required sample size to estimate a population mean would be this. N is equal to z of alpha over 2 times the population standard deviation divided by the margin of error. That whole thing is going to be squared. Okay? And of course your z of alpha over 2, that's these critical values that I talked about here for z in the last video. So you'll use that. So let's say in this particular situation here, in order to estimate the mean amount of time computer users spend on the internet each month, how many computer users must be surveyed in order to be 95% confident that your sample mean is within 11 minutes of the population mean? Assume that the standard deviation of the population of monthly time spent on the internet is 222 minutes. What is the major obstacle of getting a good estimate of the population mean? Okay, so in this case here, we have a 95% confidence, or we want to be 95% confident. That means Z of alpha over 2. Let me go ahead and pull that table back up. 95% confidence means that your Z value is 1.96. Okay? So here, Z of alpha over 2 is simply 1.96. And the margin of error is 11. That's given to us in the problem. We want to be within 11 minutes of the population mean. So E is 11. Your population standard deviation is given to you as 222 minutes. Okay, so we're only finding the required sample size. So here, that population standard deviation is known. Okay, so in this case here, this is where we use the formula. N is equal to Z of alpha over 2 times sigma. All that's divided by E. This whole thing is squared. So in this case here, Z of alpha over 2, that's your 1.96, times sigma, which is 222, divided by E, that's 11, and that quantity is going to be squared. And like we did in the other sample size required for a population proportion, we're going to round up to the next larger whole number. So let me go ahead and add this to this. Okay, we round in to the next larger whole number. Okay. So in this situation, we'll just type in this expression as is. So here, left parentheses 1.96 times 222 divided by 11, close your parentheses, and then hit the x squared button to square it. So your expression should look like this on the screen. And then hit enter. So this will be 1564.71. But you know, you have to, since you have a decimal value, you round up to the next larger number, so it'll be 1565. Okay, so in this case here, the required sample size that we need for computer users to be surveyed in order to be 95% confident would be 1565. Okay, so this should be enough to assist you with some of the homework problems that deal with a confidence interval estimate for a mean, for a population mean. And that will conclude this video on estimating a population mean.